So anyway, I'm going to talk about progressive knowing, basically. And I famously said that, from the title of the talk, that first-order logic is in for being right, stabbed with the steely knives, right? But we know from Hotel California what?
You can't hold it out. I can't remember.
You can check in, but you can't check out.
We check in, can't check out. Okay, we stabbed it with its steely knives, but we just can't kill the beast. Right. So you will get to decide by the end of the seminar whether or not I will definitely stab it with my steely knives. We will get to decide whether or not I killed the beast. Okay. So we began with our good old friend, the natural numbers, right? And so 0 is a natural number, and we're going to do all of this using types, not using sets. And Russell famously started off using types, but then most of the people then switched over to sets. But we're going to stick with the types because the types will do for us things that the sets can't. So this thing says, well, 0 is an n. N is our standard symbol for the natural numbers. It starts with. Yeah, that's plus sub 1. That's the successor. That's the plus 1 function, right? Yes. So if I is a natural number, then I plus 1 is a natural number. Okay, and it turns out there's no natural number whose successor is 0. That's also an axiom. And if the successor of I is equal to successor of j, then I is equal to j, namely successor is 1 to 1. And then we come to the biggie, the induction axiom. And this is the big one. This is the big induction. It says for every proposition P, if P is a proposition, if P, okay, goes from and into propositions of order 1, this is a standard notion for a function space in type theory. Then if P of 0 holds, and if for all I, if P of I holds, then P of I plus 1 holds. If that whole thing in parentheses holds, then we have for every natural number, P of I holds. Now, this is not first order. Because when we say for all P, we really mean all of them. All uncountably many of them.
Now wait, why is it uncountably many?
Because
uncountably many propositions, right?
Yeah, but even if there are only 2 propositions, there'd be because 2 to the nth is uncountable. In other words, a set with 2 elements to the power n is uncountable. All the functions from a set with 2 elements, okay, from n into 2 elements, that set is uncountable. So this is for all uncountably many such propositions.
Why do you need to invoke an uncountable set? You're defining the ultimate countable set.
Well, we will come to that. That's when we start to stab the beast. What we're trying to do now is say what high order logic is like, and what the deal is for all means for all propositions, right?
Not for all sentences of the language. Not for all sentences of the language. For all propositions.
For all propositions, all uncountably many. Now, for example, I might have, for each real number, I have a proposition, P of I, if I is equal to that real number. Since there are uncountably many real numbers, there are therefore uncountably many propositions. Lots of them, which turns out to be a good thing, as we will see. Okay, so it turns out that unlike in first order logic, that is categorical for the natural numbers. There's a unique isomorphism I, okay, defined for I goes from n into x for any type x, such that I of 0 of the natural numbers goes to the 0 on x, 0 of x, and the successor of j, I maps the successor of j to the successor of in the x space of I of j. That inductively defines I, And then I is defined on N. It has all the properties of being a unique isomorphism. It's defined on N. It's 1-to-1. It's on to X, okay? It's a homomorphism. It maps 0 to 0, and it preserves the successor function. And also, its inverse is a homomorphism. Its inverse maps the 0 of X to the 0 of N, and its inverse preserves the successor function on X. And if G is an isomorphism of N with X, then G is equal to I. So this was done by a fellow named Richard Dedekind in 1888. And what he did was he nailed the natural numbers. He did it, right? This is not possible to do in first-order logic, as some of you may know. And not only that, but Dedekind also nailed the real numbers as well. He axiomatized them up to a unique isomorphism. Good work, Richard. Ricard? Yeah, maybe it is Ricard. Dedekind, anyway. Ricard, yeah. Okay, so now that's great. However, it turns out that the theorems are not computationally enumerable by an argument due to no less than Alonzo Church, who published it in 1934 in the American Mathematical Society. And then Gödel came to visit, and they promptly forgot about the result for umpteen many decades. How can this happen, right? We don't know. Because it's a really...
How can theorems not be computationally enumerable? Because you're supposed to be able to test whether something's...
Well, already we know that we have uncountably many axioms.
No,
Because there's an axiom. Yeah, we do. We have uncountably many axioms.
The schema only is for...
There's no schema here. This is an axiom. We will come to schemas later. This is an axiom. There are uncountably many instances of this axiom.
Yes, but when you write down a proof, there's only countably many strings.
That's right. That means that it's going to turn out that there are proofs that cannot be written down using strings. Okay, that's one of the little paradoxical aspects. Really bothers some people.
That's not what I...
That's right. Some people.
I thought proofs is being...
That's right. That's right. Yeah. Exactly. That's what really bugged people, and that's why also I think that's one of the big reasons the result got lost. Okay, and certainly it was the reason that Gödel and all those guys went into first order logic. Right, was they kind of implicitly knew that that in higher order logic that the theorems are not computationally enumerable, and as Church says in 1934 paper, that means our field is impossible, right? We can't go there, so they didn't, right? However, it turns out the dragon comes around and bites its own tail, as we'll see in a little bit. So he had this extraordinarily simple proof. This slide is a little busy.
That does look extraordinarily simple.
But it is. Okay, so what I'll do is I will explain the proof in words, right? And then you can stare at the text, okay? Suppose that the theorems were computationally enumerable. In that case, you could enumerate the proofs of a whole bunch of theorems, right? Lots and lots of theorems. Countably many theorems. In fact, you could even prove that certain procedures are total, that for every integer input, it gives you an integer output. You could actually prove that. And in fact, in piano arithmetic, you can prove that for primitive recursive functions, for those of you who know about such things. But you could do it more generally, right? But now if you could do that, then you could computationally enumerate all the provably total recursive functions. Now, if you can do that, then you can define the diagonal procedure. The diagonal procedure is the ith provable total recursive function on input I plus 1. This little bugger, the diagonal procedure, is a provably total recursive function that isn't 1 because it's not in the list. So using techniques like the ones that Shanker used, we can actually formalize that, right? So we can formalize this, right? But it's an extraordinarily simple proof, right? And it doesn't take much to prove this. So, and at the end of the paper, Church finally says, well, you know, since there's no problem with this proof, we have to accept it. But that doesn't mean we can't ignore it, and that's what they did. Okay. So that leads you in an interesting situation. Can you ignore it? And it turns out that you can't. Why? Well, first of all, the good news about higher order logic. Well, for one thing, we can formalize the notion of proof, and that's this famous double turnstile, which kind of means proved, but which kind of means true. So phi and psi is true just in the case that phi is true and psi is true, right? And down here a little bit further, for all x, p of x is true just in the case that for every x, p of x is true. So truth or satisfiability is known as logic, is just what you want it to be.
What are the types of the?
They're propositions. Okay. But then, in higher order logic, if it's true, then it's provable. Okay. If you set up the machinery for doing the truth part of it, okay, then you set up the machinery for proof by contradiction for the provability part of it. And this is completely different from first order logic. And the net result of that is that you have inferential decidability in higher order logic, right? Okay. So either psi is provable or not psi is provable in this higher order logic, which is completely different from where Gödel was going with his undecidability, with his incompleteness result.
Don't you note, this is provability in this extremely extended sense.
That it is indeed. This is provability. This is provability, where there are proofs that cannot be written down using character strings. Now, as a practical matter, that doesn't seem to matter one little bit, because we prove everything we want to prove, with the possible exception. With a possible exception, okay. With the possible, well, for example, this works very nicely for proving Fermat's last. Okay. Now, it's true that there are still there's still some cases that we don't know whether psi is provable or not psi is provable. The continuum hypothesis is a famous example of that.
Yeah.
We don't know which one it is.
Wait. You're at the gnats.
We're at the gnats. Gnat is extremely powerful because of that.
Yeah.
That
You haven't actually given. Have you got enough machinery as it is?
well, with the type theory, you do. Yep.
Yeah.
With the type theory.
With full type theory.
With the full type theory, you do. That's right. Yep. But good question. So this is a different land than first order logic. Okay. However, this is where we're going to have to end up. It turns out, if our knives can kill, our steely knives can kill the beast, right? We will be forced to do this, right? Okay. So we can formalize other things beyond the natural numbers, right? These things called actors. Okay. So an actor is a very simple computer. When it receives a communication, it can concurrently send communications to other actors, create new actors, designate how to handle the next message it receives. So what could these actors do? You could, with actors, you can do things like you can do a readers-writers scheduler. A readers-writers scheduler is something that sits in front of a database. And what it does is it schedules the readers and the writers that are going into the database. And the rule is you can have multiple readers in the database at the same time, but you can have only one writer. So writers exclude writers, writers exclude other readers, right? So here it is, okay. And it's done as a block of cheese. Where Swiss cheese with holes in it. Because what you got to do is you got to allow multiple readers into the database at a time. So a reader can come into this thing, right, and then go into the cheese. Well, when it goes into the data. When it goes into the database here, where it says the resource.read, right, you have to release the thing so that other readers can come in and get queued up. And you also have to release it so writers can come in and get up. So the deal is that you have holes in the cheese, and so you release the cheese. So only one activity can be in the cheese at a time, okay? But the cheese has to have holes in order to be reasonably general, right? And also, if a reader comes in when there's a writer in the database, then this reader, okay, can't go in to the database. So the reader goes into a queue. It goes into the reader's queue, and that's also a hole in the cheese. So this is the kind of things that actors do. Okay. So there's an induction principle for actors, just as there was for integers. It says that if we have a proposition P that holds initially for the actor X, and it always holds when the actor X receives a communication, then it holds afterwards when it releases the cheese, then by golly, the proposition always holds. It holds every time it receives a communication, and it holds every time afterwards. That's the induction principle. And using that induction principle, we can prove.
What's the exponentiation of B? I mean, what's the exponent?
I don't think this is all predicates from behavior into propositions of order 1.
No,
so
that I get, but what's behavior?
What behavior is, just a second, behavior is something like this. An invariant. See, this block of cheese for the reader-writer has an invariant. Namely, if you're writing, then the number of reading is equal to 0. That's an invariant on the behavior.
So a behavior is, roughly speaking, the execution of a program.
The behavior is the procedure that it's going to use to process the next communication. And that keeps changing.
Yeah, okay.
Okay? But regardless of how it changes, the following invariant holds. If you're writing, then the number of reading, if writing is true, then the number of reading is equal to 0. It's true of all the behaviors.
It's like a continuation.
Except it hops around between hole to hole.
Jumps.
It jumps.
Okay.
Okay. And so, here. Okay. And so we can make a categorical theory, okay, for actors in the same way that we did for the natural numbers, right? So we'll have a unique isomorphism, okay, and it has all the right properties. So then this means that we can, using higher order logic, we can characterize actors up to a unique isomorphism in the same way that we did for the natural numbers. We cannot do that in first order logic because there'll always be these non-standard models lurking around. For example, for the integers, if you have a first order axiomatization, right, then one of the models, well, you have models with infinite integers in them, and with some integer that's bigger than any integer you ever heard of.
And its successor.
And that's right, its successor, that's right. Okay. So So that's different from, now we're getting out our knives to kill the steely beast. First order theories are different, okay? We don't have one of these very powerful induction axioms for which there are infinitely many instances. Instead, we have schemas, okay? And we use schemas for countably many computationally enumerable axioms, and the theorems are computationally enumerable. So this was goodness and light, the way that Hilbert thought things were going to go, and the thing that Gödel believed in, and the thing that they forgot about was that when Church's result was thoroughly and deeply buried. So now we have an induction schema. Okay. We're not going to do it for all propositions from n into propositions n or 1. Instead, P is a string for an expression for a proposition. We need strings so that there'll only be countably many of them. Okay? And then what we do is we abstract from the string to the proposition so that we can have, right, countably many axioms, right, of this induction schema.
It's not just that there have to be countably many, only countably many strings. It's that you set the thing up so there are only countably many.
That's the way we set it up. That's why we say P had to be a string for an expression for a proposition.
It could be a string for every real.
Yeah. Actually,
strings are finite.
This is never mind. Okay,
Strings are finite by your
right.
Yes, it's the standard, yeah.
Right.
Each
Yep.
string is finitely long, and there are only
Finitely many symbols in the vocabulary. That's right. Yeah. Okay. So now we need an extension schema, as you typically do, because we're going to need some sets. We build our sets out of propositions, right? So we say that for every proposition, there's an extension, so that you're in the extension if and only if the proposition holds. And there are countably many of these. That if you go look up ZFC, this is called the extension schema, right? It's in the Wikipedia, okay? And we want to know something about these things. We want to know that for any set of integers, there's a least, any non-empty set of integers, there's a least one, right? We need a little bit, in order to kill the steely beast, it has to have some power. It has to be what we call moderately powerful. Okay, so we give it some sets, and we tell it that every non-empty set of integers has a least element, just so we can prove something. And if we do that, then we can prove something. We can prove something you can't prove just using the induction schema. Namely, we can prove that the Ackermann function is total. Okay, which is not provable only using the induction schema. Turns out that Gödel proved that. Okay, but now we have Church's paradox. Okay, remember that argument we went through that Church published in 1934? Now we have enough machinery that we can carry that out in first order logic, but with one crucial difference, namely this theory, nat1, which is first order nat, with these axioms, can now prove that its theorems are recursively enumerable. It can also prove that its theorems are not recursively enumerable, right? So if these steely knives stick, then first order logic is in deep, deep trouble.
Meaning what?
Meaning that if you have a moderately powerful first order theory, like...
So one thing, it's first order theories you're talking about, not first order logic.
Yeah, but we only care about first order theories.
No, that's okay. I'm not actually...
Well, and we only, and what I'm saying, yeah, right.
To get the language.
Yeah, right. So here's the picture. Here's the picture, okay? We're looking at first order theories. They can be they can be narrow or wide. They might only be about some narrow thing, or there might be wider things. Okay, they might be in terms of power, that they may only have small power, or they could have great power. So here's the picture. As soon as you get to be moderately powerful, you are inconsistent.
So how do you define power?
Power means this: you have the induction schema, you have the extension schema, and you have the least element schema. You know some very elementary things, and if you know that, or you have some axioms that can give you the functional equivalent, then you can do Church's paradox and generate an inconsistency. So this is hacker's paradise. We'll come to hacker's paradise again later when we look at deep learning. Okay, so that's the basic problem for first order logic, right? Is that once you become moderately powerful, right, you're inconsistent.
It's not the basic problem for first order logic. The basic problem for first order logic is it can't represent dozens of things in the practical world that we need to compute.
Well,
That fact about first order logic makes very little practical
that's
difference.
true. Okay, that's right. But suppose you decided to put in some axioms into first order logic so you could compute these things. Then you'd become moderately powerful and you'd become inconsistent and you'd be dead. If you try to soup up first order logic so it can do something reasonable and it becomes moderately powerful, then you are dead.
You're dead anyway because you can't do enough reasoning.
That's skipping to the conclusion. Yeah.
Keynes said in the long run, they're all dead.
We're all dead. That's right.
Well, thanks.
So what do you think, Shankar?
I have my doubts about whether there is. I mean, first of all, you're adding some new principles to.
That's right. We are. Yeah. The question is there something wrong with the extension schema, which everybody puts into ZFC, right? Everybody puts into ZFC. Is there something wrong with the principle that any?
Is that your version of the separation schema?
It's sometimes called the separation schema. Yeah. It says that for every one of these little predicates, right, that we have a set. And this one says that for any non-empty set of integers, there's a least element. So these look like they're pretty innocuous. There still are extensions. That's right. Now we need that. Like, why do we need that? The reason we need that is because we need this. We need to be able to prove that certain procedures are total, like Ackermann. In particular, the one that we need to prove is total is the one where you diagonalize. Namely, you say the ith provably total recursive function on input I plus 1. You have to know that diagonal. You have to be able to prove that diagonal procedure is total, and it's not primitive recursive. So you can't prove it in what's called piano arithmetic, which only has the induction axiom. So we're going to, in order to get the inconsistency, we are going to have to soup up things a little bit, but not much.
No, right. But so as I understand this picture, your claim has as a corollary that all versions of set theory should be.
No, because ZFC cleverly left out the induction axiom.
They didn't leave out the induction axiom for arithmetic.
They did. ZFC did.
No, it's not one of the axioms.
That's right.
But you can prove it.
Are you sure? Okay. Well, then it may be that this result will generate to ZFC, but I'd have to take a look at it carefully to really make sure that you can prove that induction schema. You have to prove the whole schema.
I mean, I mean, ZFC includes full second order arithmetic.
No, it doesn't.
So,
Yeah.
setting that
Go ahead.
aside,
Setting that aside, yeah.
You know, I mean, you're going slightly higher order with this extensionality.
Well, it's not higher order because we're trying to give first order logic the benefit of the doubt, in the sense that we still want, we're trying to go as far as we can and still have the theorems being computationally enumerable, right? What can you do and still have the theorems being computationally enumerable, or do you really have to go higher order and give up on the theorems being computationally enumerable?
So again, I mean, with higher order logic, you know, there's the kind of normal, it's a standard interpretation. That is, you know, it's the A arrow B is the set of all maps.
We're doing. That's right. That's right. There's also a hack that Henkin thought of called the Henkin interpretation, right? Where for all doesn't mean for all anymore, right?
But the issue is that, you know, as far as axiomatizability, you know, it's only complete with respect to the Henkin interpretation. It's not complete. I mean, higher order logic is not complete.
Well, that's the crazy thing, is that, yeah, with a higher order thing, you do get, which the people kind of know, but nobody ever mentions it, that you really do have, that if it's in the higher order system, if it's true, then it's provable.
That's with respect to the Henkin interpretation.
No, that's with respect to the standard interpretation. Yes, it is. No. This is the one where for all means for all, right? So let's see. Yeah, here, this one, where for P, we don't mean the Henkin cut down ones. Okay, we mean for all P, all uncountably many. In the Henkin one, there are only countably many.
So I take it this is supposed to, I mean, this is a version of the, as you say, categorical second order axiomatization of arithmetic.
That is correct.
Yeah.
Right.
Which
With the standard interpretation, where
yes,
P means for all P.
We agree.
Yeah, we agree. Okay.
And
It's incomplete.
And that's incomplete.
Sorry, Charlie. It is complete by a very, very trivial proof. Very, very unfortunately complete. Okay. It's ridiculous. Okay, here's the deal. You want to see the proof?
Yeah.
Proof by contradiction. You know how proof by contradiction goes.
I've committed it many times.
Suppose we've got that psi is true. Suppose, just for hypothesis, suppose that psi is false.
Suppose that it's true.
No, we're going to prove that psi is provable in NAT using proof by contradiction. To do that, suppose that psi is false. Do you see the ground, the ice crumbling underneath your feet yet?
No.
No, you don't. Okay. We have supposed that psi is false, and our hypothesis is that psi is true.
By standard reasoning, you can prove anything.
Now, this means that we have what's called a contradiction. And by proof by contradiction, we have now proved psi in NAT. It's ridiculous, but it's valid. How did this happen to us, right?
If I go to all this trouble, why not just say, okay, assume P.
No. This
Assume
we're
not
proving
P.
it. We're proving. No. You have to pay attention. You have to pay attention. We have a hypothesis that C is true. Our conclusion is that psi is provable. In order to prove an implication, you get to assume the hypothesis.
Yes, I'm assuming.
So let's assume that psi is true. Now we're going to prove that psi is provable using a proof by contradiction. The way that proof by contradiction in NAT works is we get to assume not psi and hopefully derive a contradiction. Fortunately, there's one very close at hand because we know that psi is true. So you're using the natural. This is a perfectly valid proof by the Joukowski natural deduction proof system. Now, how do we get away with this? I mean, Gödel had something to say about this, right? So let's keep going. Okay.
Double turnstile
Okay.
is true, right?
Goebbels turnstile means it's true. That's right. Okay, so Gödel. Okay. Gödel has this famous sentence, I'm unprovable. Okay. And here we have it here. It's defined by I'm unprovable if and only if I'm unprovable is not provable. That's the defining characteristic of I'm unprovable. So Wittgenstein comes along, okay, and he goes through this little thing, right, where you manipulate the thing in Nat 1, right, and you can derive an inconsistency. And so Wittgenstein's conclusion was that's what comes from making up this kind of proposition. Don't do that. That was Wittgenstein's conclusion. Don't do that, right? What was Gödel's response, do you think? First of all, Gödel said, Wittgenstein's crazy. Then he said, you may have thought that my 1931 paper was about Principia Mathematica, right? Even though it says it right there, yeah. Nah, no such luck. No. My proof was actually about, okay, a fragment of a first order theory. That's what my proof was actually about. Therefore, Wittgenstein is crazy, and there is no problem. However, there's a problem. So what do we do about I'm unprovable? Well, we've got types, right? So I'm unprovable is constructed using what's called the diagonal lemma, which is a fixed point construction, right? Where you map as up proposition P, you map as proposition P into P is not provable, and you take the fixed point of that, and that's the way you get I'm unprovable. But once you go to strongly typed theories, P is a proposition of order n, whereas I am not provable is a proposition of order n plus 1. So there is no fixed point.
I thought all these things were about numbers. So
they're all about numbers.
Right.
Everything is of the same type. They're all numbers.
That's right. That's right. We're definitely changing the rules here.
Yes,
Right?
you are.
We are. We're changing the rules, saying that everything has to be strongly typed, right? And
you have to
and
take away the machinery necessary for arithmetization.
And we've done that in a higher order logic because we have done that because by brute force of having all these uncountably many instances of the induction axiom, we have by brute force taken away arithmetization.
Yes, you can't arithmetize.
That's right. That's right. You cannot. That's right. Yeah. And so, but nevertheless, we'd like not provable to be a perfectly decent procedure, which it is. But it doesn't lead to any problem because there's no fixed point. And as a result, Nat can prove its own consistency without trouble because I'm unprovable has gone away. We have killed it with our stealing knives. We have killed I'm unprovable. And so Nat proves its own consistency by the same ridiculous method. Suppose that Nat is inconsistent. Then there's a proposition psi, okay, such that you can prove psi and you can prove not psi. Let's use those theorems in our proof. Now we have psi and not. So we prove consistency by proof by contradiction. We suppose it's inconsistent. We will derive a contradiction. If it's inconsistent, if nat is inconsistent, there's a proposition psi. You can prove psi and you can prove not psi. Let's use those theorems in our proof. Now we have psi and not psi. That's what's called a contradiction. We're doing a proof by contradiction. Consequently, nat has proved its own consistency, and this is okay. This is a non-Gödelian world, okay? In the same way that relativity is a non-Newtonian world, and in the same way that quantum mechanics is a non-Einsteinian world. However, if this is where we are with first-order logic, then for computer science, since we really want to have moderately powerful theories, first-order logic is not an option. So, welcome to the brave new world of stealing knives.
But we do that by trying to solve real-world problems with it and not quite getting there. So,
Kiss isn't the man.
Oh, yeah, that's a bug. That is a misspelling.
I assume it's Chris.
It's Chris. I could actually fix that. I think. Oops.
Kiss is not a man. Well, this is San Francisco, so it doesn't.
Well, no, I can't. I'm in. Okay, so Kiss. Yeah, Kiss is not a male. Okay. Why is Kiss not a male? Because Kiss is a person who identifies as female, and therefore a female is not a male. Okay. On the other hand, our friend Kiss here is a male. Why? Kiss is a male who has male chromosomes. So therefore, Chris is a male, and so therefore, Chris is both a male and not a male. Okay. Get over it. Right. That's right.
Say to evangelical Christians.
Absolutely. Get over it. And this is the state, okay, of our information and our knowledge bases. It's full of this kind of stuff.
So, but this gets back to his point.
That it does
It's
indeed.
not a fancy. You don't need any fancy story like about whatever the story was about second order arithmetic. It just, yes, you have attributions to people of what look like contradictory properties.
This is a straight up inconsistency.
Well, it's not really, if you think about it.
Kiss is not a male and Kiss is a male. That's a straight up inconsistency.
But there are those things in the middle. The mediating properties in the middle. One has to do with chromosomes. The other has to do with self-identification.
Right. And what that means.
Why should they go together?
And what that.
Lots of people they do.
Yeah.
Some people
that means we have two arguments. We have this argument for Kiss as a male, and we have this argument for Kiss as not a male.
Yeah.
And we'd like to have both of them in our system because, you know, we kind of, yeah.
I agree. I'm for that.
Yes. So once we have both of them in our system, then we have in our system a straight up inconsistency.
No, that's a misleading.
And so one option that we have is to modify the laws of logic so that this doesn't blow up. If you put this into OWL, guess what happens? OWL is first order. OWL blows up.
Why wouldn't you want to have two notions of gender? One application.
For
and there
instance,
are
there's one way.
genetic
That's
changes,
one way to solve it.
then you.
Well, that's what Doug Linott thought. And that's what I thought too. And back to 1973.
That's not by itself an argument against it.
That's right.
Having said that, it's kind of an argument, but it's not a conclusive argument.
We had this idea of islands that we were going to differentiate, right? And then we found out that we were in the same problem that our fellow software engineers were in, right? Yeah, that's right. That was a reasonable thing to think in 1973. We'd have these islands of consistency, and then we have these axioms that connected the islands of consistency, right? And we would do artificial intelligence. That's what we thought
That was actually a perfectly good way to think about it.
at that time.
No,
Now what
no.
it turns out it has not worked after these many decades. So what was the problem turns out to be the same, is that we have the same problem here that the software engineers work. That was what, people like Turing originally thought, that we'd have these programs, we'd prove them correct, and everything would be perfectly consistent. Guess what, folks? In case you haven't noticed, it hasn't worked out that way. We have this software that's got more inconsistencies than we can count. And we can't stand calling them inconsistencies, so we call them bugs. But
that idea, the original intuition, that as you put it, that people like Doug Linott and yourself and Minsky and all these other.
Well, Minsky was dubious, I must say. He was smarter than both of us.
Well, at least not in the frame. Well, neither in the Frames paper nor in Society of Minds was he dubious. That is, the picture is you've got these different ways of thinking about one and the same object, and they're just different. Never mind why they're different, or even in detail how they're different. They're just different, and yet you got to be careful about combining.
We come from different points of view.
Yeah,
There's
yeah.
information that's in
There's a whole field at Stanford called gender studies. Okay, do you know how many ways you can parse this diagram? Do you know how many different senses of maleness there are?
I'm old. It took me a while to realize there are at least two. I'm old, although I'm from the 60s, so maybe I did realize it even before.
So
The process that those people undertake to parse out maleness is a reasoning process. It's a reasoning process which involves making and dicing up definitions. It's a process that would have to be done before a good diagram like that was created.
And we said we'll just dice it up in our software. It turns out the dicing cannot be done.
Right.
No. It's not that the dicing can't be done. This is just like what people thinking about, parallelism realized. You can't always put diced things together safely.
Yes.
It's not the dicing itself that's
So so our proposal is give up on that and put all your nicely undiced things together in one big pot called the big ontology, which has to be inconsistency robust. This is another strike, perhaps the most deadly strike, against first order logic.
So it's consistent.
Because it blows up, OWL blows up, if you have a single inconsistency, even if you don't know where the inconsistency is. Okay, it's just like first order theories blew up as soon as they became moderately powerful. In which Church noticed the inconsistency in 1934, and then until the computer scientists actually wanted to use first order logic for things that are moderately powerful, actually use it in practice, it didn't matter. But as soon as you did, even though you hadn't noticed the inconsistency before, you're dead.
But how would you use higher order logic if you want to have uncountably many axioms, when in a computer you can only represent countably many.
Yeah, well, it turns out all the proofs that we do using higher order logic, okay, have perfectly good proofs, okay, that are represented in character strings. So there's actually a mystery here. Please, ye brave mathematician out there, characterize the theorems that cannot be proved using character strings. We would like to have a characterization. We know they exist, okay?
But you've moved on to the cool practical aspect of what you're trying to do, which is you've got a mess of in the ordinary sense, not in the Gödel sense, inconsistent information in a database. You still have to reason using that inconsistent information.
That's right. So we have to change the laws of logic, and that's what we've been doing at Stanford for.
Change the laws of logic.
So we have a book about it called Inconsistency Robustus.
Change the laws of logic, or you could add other algorithms that would help you, just like the gender studies do. All of gender studies people do all of this hand bringing and all of this other kind of reasoning to resolve what maleness is and what femaleness is, or not to have it at all.
Guess what? You know what? I have never seen any resolution. I've been to long meetings in gender studies. There is no resolution.
Well, the computer would have to do the best that it can.
That's right. Here's the best that we can do. We create a big ontology in which we put everything. And we modify the laws of logic so we can still reason about this stuff without blowing up. I'm not going to tell you exactly how we do that. It's pretty technical. It would take another hour to explain how we can do that, but we can do that. So now we can reason about inconsistent information. We can reason about kiss being both a male and not a male, and that being an inconsistency, and that is okay. The system does not blow up. The machine does not become confused. You cannot derive everything from this. This is the approach being recommended. Throw it all into one big pot, change the laws of logic, right? Never mind Euclid and 2,000 years. But that work is still valuable. And the way you preserve that work is you put it into higher order mathematics so you can have some power. And that is consistent. So you have a consistent theory of the natural numbers. You have a consistent theory of actors. You have a consistent theory of the ordinals. You have a consistent theory of the real numbers. You have a consistent theory of set theory. And you build your big ontology on the top of higher order mathematics, and you want higher order mathematics to be consistent. Why do you want higher order mathematics to be consistent? The reason you want higher order mathematics to be consistent is so that when the big ontology builds on them, you don't have inconsistencies leaking through from the higher order mathematics into the big ontology. You don't want to have that leakage. No leakage of inconsistency from your mathematics, please. So the higher order mathematics is consistent. We preserve the work of Euclid and all of his successors. We build on that work in building the big ontology.
People have resisted high order mathematics because they feel it's just too difficult. It's too hard.
People said the same thing about quantum mechanics and general relativity. As Achilles famously said, the tortoise famously said to Achilles, you know about Lewis Carroll, then logic will take you by the throat and force you to do it.
Oh, by the way, you're going to kill deep learning for us.
It's coming right up. Okay. What do you think? Is that a cat? Nope. Toaster.
It's a picture of a cat.
It's a picture of a cat. It's a hacked picture of a cat. It turns out there's this whole technology now for making tiny little changes in pictures, and you get the wrong result. The hackers are onto this. They're doing it for spam filters now. They hack the spam filters. They make these tiny little twitches, and it comes out not spam. Okay. And that's because these deep correlation engines, okay, these multi-level networks, right, do not have a theory of a cat. Okay, all they have is a big corpus and a set of levels of correlations, right? And these things are eminently hackable. And if we try to base our intelligent applications on these things, we are going to be hacked like crazy because it doesn't have a theory of a cat. The deep correlation network, okay, doesn't know that cats have 2 eyes. It doesn't know that they have 4 feet typically. It doesn't know that they have tails. It knows basically nothing. It does not have a theory, okay? It lacks modularity, and it lacks argumentation based on evidence. And these are the tools that we have for building our intelligent applications so that they are not hackable. And in case you haven't noticed that, one of the biggest problems our society has now is our software is all too hackable. And if we're going to make intelligent applications, okay, they better not be as hackable as the current stuff is now, or we are in deep trouble.
I just come from a talk where some guys caused a car wash to become violent and smash cars. It's quite
Yep. Oh, you know, they've hacked automobiles to, you know, you stand by the side of the road and turn on the brakes. We've got to do better, my friends. Look, if the bridge builders were doing as badly as they would be hung from the lamppost because all the bridges would be falling down, right? We computer scientists, we're just not measuring up as engineers, as a profession.
You would call it common arrows. You're allowed 1 failure.
Common arrows? I don't know this.
Common arrows.
Oh, common arrows, 1 failure. That's right. Yeah. Yep. They learned. That was the bridge where the wind came up and it. Tacoma arrows. That's right. Okay. So we have to do better. Okay. So there's an interesting parallel here with natural law. And John Woods is an excellent philosopher, has written this paper that's going to be published in a book next year by college publications titled How Paradox Fails in Inconsistency, Robust Logic, and Beyond. Computational and Naturalized Approaches. It'll be published in Studies in Logic next year. It'll be the successor volume to our Inconsistency, Robustness volume. Okay. So he says, logicians of inconsistency robust logic and logicians of naturalized and empirical leanings have enough in common to warrant a working alliance or anyhow a limited liability partnership. And I think he's right, that we have something to learn from these guys. Because you see, the myth of United States law is the axiomatic link myth, namely the Constitution and the laws, and everything is derived from that. Whereas in English law is judge-made law. They have no written constitution, right? Everything is based on argumentation and evidence and precedent. Now, in second-order logic, we seem to be wandering into, or the higher-order logic, we seem to be wandering into their territory. Because now we can no longer computationally enumerate our theorems. Just like in the English law, there's no constitution and no body of law from which you can enumerate the conclusions in any kind of sense. It doesn't work like that.
Yeah, we use shadow of a doubt kind of things. So we use very fuzzy, probabilistic, whatever, uncertain boundaries.
Right.
And everybody lives with that. They're quite happy with that.
Right. So I think John Law is onto something here, and we should take him up on this offer of a limited partnership and work with the legal scholars and the philosophers to make sense of what we're doing. So I think that we're into the business of progressive knowing, and progressive knowing is argumentation based on evidence. This is our touchstone in logic, in law, in philosophy, in everything. The alternative is what we call lying, which is attempting to deceive. Tactics are shoot the messenger, okay? Shut down the press. Whataboutism, right? If somebody says that Putin hacked our election, you say, what about Benghazi? Benghazi, Benghazi, okay? And outrageous trolling. If you can get somebody to talk about the ridiculous thing that you've said, then they won't focus on what's really going on. All of these are attempts to deceive, and John Oliver has an excellent program on that, which I highly recommend to you. So that's the conclusion. I think that the alternative to progressive knowing, the absolute alternative is lying, the attempting to deceive.
Would you now recommend statistics as a valid approach?
Statistics, I think that statistics are going to be extremely important right here in the big ontology. The big ontology needs to accommodate statistical information. You see, the deal was that one of the things that was supposed to happen here with the deep correlations was a kind of an attempt at inconsistency robustness, right? Because it is able to overcome some inconsistency. However, it doesn't do a very good job of it.
You didn't ask the problem posed to the deep neural network with these pictures is not recognize cats. It's recognize things that are similar to this set. Okay. It's not, they're not asked to recognize.
Well, this is a classifier. It was classifying cats and toasters and other things.
Well,
And it turns out that it's eminently hackable.
it is hackable, but what you're saying is correct. It's not answering the question, what is a cat? It's answering the question, is the picture, the new picture that she gave me, similar to the set of pictures?
Yeah,
that
the
have
class. Yeah,
cats?
it had a whole corpus of stuff, right? And it was claimed to be very good at recognizing cats and toasters and dogs, right? So we took one of the pictures of the cat, we hacked it, and it came out toaster. This is not good.
In the past, you always talked about statistics as being virtually similar to lies, and now
No.
well, that's why I'm in your.
No. Statistics is a valid field of knowledge. Okay.
Okay.
You right. Yeah, and there's a famous book, How to Lie with Statistics. Okay. So statistics is another way of dealing with inconsistent information. You can try to statistically smooth it. Okay, and that has to be a very big. That has to be a part of the big ontology. They have to take that stuff in, right, and put it into the ontology like everything else.
If I understood you right, you just said we need probabilistic things, statistics. We need high order logic in order to represent things, which is
well, the probability is a whole other can of worms. You certainly need statistics. No question you need statistics. So what do you think, Shankar?
Can't disagree with much of this, but the argument based on evidence still might not fly, because there's this other objection which is based on grasping at straws. And so, take climate change. Someone could say, oh, this is just something temporary, or there's no evidence for it.
Right. So sorry.
Reacting to something that just happens in nature is, hurricanes. It's just a
Yeah, I think Shankar has a very good point. There's good evidence and there's bad evidence. You can fake evidence. There are good arguments and there are bad arguments, right? So it's not an absolute guarantee path to success, but I think it's the approach that has the most promise for our intelligence applications. Is argumentation based on evidence is the paradigm that we should follow.
Yeah, but there's, both sides will say we can cherry pick the evidence and
You can cherry pick evidence and you can have bad arguments, but that doesn't mean that you're not in the arguments based on evidence game. That's the competition.
Could you go back to the slide which had the males, definitions of the male?
They're not definitions.
Well, they are and they aren't. These are two representations which contradict, because one of the ways that we would sort this in the gender studies, if we were gender studies people, which we're not, would be to say that different people are defining maleness differently. And what Richard said to do was create two different definitions as a means to sort this. Okay.
Yep.
So when the
So we need to finish. Yeah, we need to finish up here. What I would say is both male and female are natural kinds. We used to think that they were quite distinct, and now we're discovering some of the subtleties involved in male and female, and it is extraordinarily complex.
In almost every application, I need to make a binary decision. Can Chris go in the ladies' toilet or not?
Right. And are you in South Carolina?
Right, can you join the army? And therefore, it seems to me that no matter what you do,
that's right.
You'll end up having to.
You'll end up having to make decisions.
That's right. So either route is going to be.
But with time, those decisions can change. It used to be that females couldn't be pilots in our Air Force. That has changed. It used to be that females couldn't be Marines. They were Marines in the Israeli army, but not our army. Now they can be Marines in our army too.
Lots of things in the world change. You have to update your model out there. You can still do that with Richard's style of.
Well, that was the great myth that we believed in, that we could get it all, we could nail it all down, we could get it all consistent. Maybe we can't. Maybe we can't. Certainly software is not going that way. Thank you.